really that's the end of the tough stuff. After that, we'll be on to still volume, but not so many concepts that you have to get a handle on. So we have two parts for this idea of light that's coming from the sun. Now, we touch this in a very superficial way. You don't have to go into deep quantum theory and find out about Schrodinger's cat or anything else. And, you know, we just want to keep enough of this information so we can understand how these things work and how they affect the gemstones. And it is important because that helps us do our identifications with the instruments next year. So with the wave theory, where we're pretending that the wavelength of light is only just a wavelength, these are the effects that we can have because the wavelengths of light are going to affect some of our gemstones. So when we do question 7, they're the things that you'll be learning about. Plasticine, chatoyancy, apterism, that's lesson 7. But if we do this first, you'll understand more about why we get these effects from the wave theory of physics. So these are just straight, simple terms. The sun is 150 million kilometres away, so any light that comes from the sun, we don't think of it as branching out. We think of it as all parallel waves of light coming from the sun to hit the earth. All, so it's not like a light bulb where the light's going in all directions. With respect to the sun coming to the earth. Anyone in trouble? So
Ana, pues salían mucho las piernas, ¿no? Yo le digo a Miklos.
There you go.
And those at home turn their mics off unless they want to ask me something, please, and ask in English. Okay, so these are the things that you need to know, the definitions of these things. Now, this is not hard. Think about the waves on a beach. What's the crest of a wave? What's the trough? Okay, so what's the difference between the top and the bottom? Not there, the amplitude. You know, like I'm just thinking of waves at the beach. If there's a big long wave and the whole wave's coming at you, what's that? A wave front, because all of the bit of wave is coming at you at the same time. Frequency, how often do the waves come to you? Do we get one every 5 minutes or do we get one every 3 minutes? That's the frequency of the wavelength that's coming your way. Intensity, how high is it? What's the amplitude? How high is actually that wave that's coming in from the beach? They are all, it's exactly the same as the waves on the beach. So when you look at these things, it should be easy. So we measure a wavelength from either crest to crest, trough to trough, doesn't matter where, because you start at one point, you go through a wave motion to the same point in the next section. So wherever you can choose from here to go through into the next one here, it doesn't matter. The wavelength is how far it goes.
Sorry, Jacqueline is struggling to get in.
She's a bit late. This is what I don't like doing. So no, that's not what I want. I want admit all. Admit. Okay, thank you, Nicole. We've got to come early. Okay, now I should be able to go back. So has everybody got my PowerPoint again at home? Yes? Can you all see? Thank you. Okay. So wave. So the wavelength of light that's coming from the sun is travelling light. So all of the wavelengths are travelling like this. Now, what do we know about the light from the sun? Is it one wavelength of light?
No.
It's hundreds and millions and thousands of them. Are they all exactly the same?
No.
No. So we get different amplitudes. We get the intensity is different. How high that amplitude from the top to the bottom is the amplitude. That amplitude tells
What is the like top to the bottom? Like what are those measurements?
amplitude.
Yeah, but like
Oh, is it hertz per something or other? I have not taken much notice of what.
what's the difference in like if it goes really high up and really low down? Like is it
That's
colour or what
intensity.
is
So in something like colour, it could be the intensity of colour if that's what that wavelength is producing. Yes.
okay?
So we are
say
going
if
to
they were like small, it would be
violet light.
okay, and then if
Oh well, we'll get to it. So
okay.
if I've got a high frequency, that means in the space of a particular time, I'm going to get lots of wavelengths. It's got a short wavelength, so it's got a higher frequency. So in light coming from the sun, we've got red, orange, yellow, green, blue, indigo, and violet. The very, very short wavelengths is the violet end. The great, big, long, slow ones are the red end. So by the time you get all of those colours mixing up in their equal proportions, we get white light. So once they interact with something like a gemstone, there will be interaction with some of those different wavelengths of light. So that's when some amplitudes might get bigger or smaller to change the value of the white light and therefore give us something like a colour. So the
Jen,
yes,
can I interrupt?
yes.
So I have a question. With amplitude, are you measuring it from the horizontal line and what's above it or below it? Because it's both positive and negative.
No, the amplitude is just, if you look in the notes, it might be clearer, but it's the top to the bottom. As far as I remember, it's the top to the bottom.
But I came into this with that question, and when I look at that scale, I see positive and negative, which makes me think.
That's only because I'm going to show you later on how if we get a wavelength that's in its up motion, its up phase, and a motion that's in its down phase, they could cancel each other out. So it's not actually about anything except having a median line there around, up and down, through which from that median line you get the wavelength happening. So it's just a mythical line through the middle when we're describing all of these things.
So amplitude would be from crest to trough.
As far as I remember, yes.
Okay.
All right, next one. Okay, so not only have we got a wavelength of light traveling like that, that wavelength of light is also vibrating in every direction perpendicular to the way it is moving forward. So while it's moving forward, it's doing all of these vibrations in all of those planes while it's moving forward. So all the wavelengths that are coming forward, all together, they're all moving together. That's the wave front. They're all moving forward, but each little part of it, this is the electromagnetic spectrum, is actually doing this vibration at right angles to the wave front, at right angles to the direction it's moving forward. So we call that unpolarized light because you're getting all the wavelengths all together in all vibration directions perpendicular to the way they're going through. So what we get onto in a little while is something like what we call a polarizer. So if I can make it somehow that light can only pass through in one direction and block all of the others, so I've got a wavelength coming through, I want to put it through this particular piece of whatever it is, but it will only let that vibration through. So by the time it's come through, it's still going to be like this, but instead of vibrating in all directions, it's only going to be vibrating in this direction as it does its wavelength. So that's how we polarize light. It's how your Polaroid lenses work, because we're actually going to block out some wavelengths of light and let some go through this barrier. So that's the difference between unpolarized and when it goes through there. And so instead of showing a wave, we've just shown a straight line there, but the polarized rays, apart from going like that, are actually only vibrating in that direction. Or if I turn that sideways, I might find as they come forward, only the sideways motion will happen while it's going like this. And so I can polarize it in quite a few different directions if I so desired. So if I put one polarizing piece there, letting through this light, if I put another lens here that only let that through that way, what's going to happen? What happens over there?
There's
Nothing.
no light.
No light, because by the time it's been polarized there and then it comes across something that's only going to let it go through that way, nothing happens. So we use that in one of our instruments in there and then see what happens to gemstones when we move it. So this idea of polarizing the light, it's actually simplifying what we're doing to the light with, if that's what we want to do. And there's a number of ways that can happen. 3 different ways, in fact, that we can do that if we want to polarize those wavelengths of light going in a particular direction. Now, the other thing that we need, and there's another diagram there if it makes it any simpler, this one here. It's the same thing, but it's just showing you how the light's vibrating, but once it's gone through again, we're only seeing it in one direction because we've got some sort of filter like your Polaroid lenses in your glasses. So if I had 2 Polaroid lenses that I took out of your glasses and I put that one that way and I put one the other way, that would block out all light. But with Polaroid lenses, we only block out some of the light and let some of the light through.
Jan, do you mind making the PowerPoint like the screen?
Oh. The screen. Sorry, I didn't put it back to, sorry, is that better?
A bit, yeah.
That one's not very good because I've taken that off the internet, and of course I might try and write that a bit better for you. So obviously that's the difference with your polarizing lens, because we've cut quite a few of those vibrational directions out. So the light that's coming through has been marginally reduced in glare.
So that means we have to be careful looking at a gemstone with sunnies on, because we end up getting a blue and blue or a red or red.
Oh well, this is the polarized version because we've cut out quite a deal of the light, and so it can cut out glare. It's like why you use glasses if you're trying to look into a rock pool. It will cut out some of the glare so you get the reflection, so you can look into it better than without.
So does that influence what you actually see then?
Well, slightly, yeah, but there's no way we'd be looking at gemstones with sunglasses on.
Oh, no, I mean,
Yeah.
I've got other lens, I know.
Well, it's giving you less light, but it's still all the different wavelengths of light coming through, just vibrating in one direction. So if you've got all the same wavelengths of light from white light coming through, but just only vibrating in one direction, all the colours are still coming through. We've just cut out the quantity of the light coming through, but not the quality of the light coming through.
That's what I mean to ask.
So this is quantity mainly that you're cutting.
I'm cutting out quantity, but I'm still got the same percentage of red, orange, yellow, green, blue, indigo, and violet going through. So the colours haven't changed, but the amount of all of those colours coming through has been cut right back. So that's the only little hard bit there. There are definitions that you can learn, so you know what your wavelength, your frequency, your wave front is. All of those things are there in your notes to learn. That's just so that you understand when we talk about a wavelength, what it actually looks like and what it's actually doing. Me waving my arms around. So this is the first important thing that you really need to look at, which is Mr. Snell. Now, Snell's got 2 laws. One's about reflection. So what does reflection just mean? Even if you haven't know the particular definition for this, what is reflection?
Light bouncing off a surface?
Exactly. Light bouncing off a surface. It hasn't, at this particular point, we're only talking like something like a mirror, so no light can go through, but it will bounce off and come back out. And Mr. Snell worked out, and once you know this, it sounds quite reasonable, but Mr. Snell said the angle of incidence is equal to the angle of reflection. Now, we have a parallel surface there, and we have an imaginary line that we call the normal at right angles to the surface of that mirror, gemstone, whatever. So that is classed as the normal, and the angle between the incident ray, the light that's going to do the bouncing, the incident ray is the angle between the normal and the incident ray, and the reflected ray is the corresponding one. So that I and that R are always the same. So if you've got a question in an exam and it says the angle of incidence is 40 degrees, what's the angle of reflection? So what's this angle here? 50 degrees. Just be careful when you read a question, because people start to think that this angle here, they think that this angle from the incident ray to the mirror is what we're talking about, but we're not. We're talking about the normal and the angle between the incident ray and the normal and the reflected ray with the normal. So his definition says the incident ray and the reflected ray are going to be exactly the same so long as they are the normal, the incident and the reflected ray are all in the one plane. If they bounce off in a different direction, well, we've got other things to think about. But so that is not hard.
Sorry, what does the normal mean?
It's just an imaginary line at right angles to the surface of a mirror, of a gemstone or whatever. When we're talking about reflected light, it's an imaginary line at right angles to that surface that's doing the reflecting. They always ask about Snell's laws in the exams, which is why sometimes your workbooks are reflecting us finding out if you understand, not necessarily all the time what's going to be in an exam. Whereas Snell's laws, I don't remember if they're in your workbooks, but they're certainly always in one form or the other in your exams.
So, sorry, the normal is in relation to the surface, so the red arrows that you saw, that's not the 90-degree angle, is it?
No,
this
is.
So we don't know what the angles are there.
No,
No,
so
right.
but it doesn't matter with respect to the equation. So if that red incident ray was down here, the reflected ray would be out here,
Right.
so that angle of incidence and reflection is always the same.
Yep.
Easy peasy. It's not a difficult concept. But if you can do it in our way, saying the incident ray and the reflected ray are equal, so long as the incident ray, the reflected ray and the normal are all in the one plane. They're the two parts for the definition you need to know. His second law is about refraction. Now, what does refraction actually mean? What does the word mean?
To bend.
Bending, to bend. Perfect. So refraction is the bending of light, because if we've got light waves traveling in the air and then it hits honey, water, a gemstone, what happens?
It refracts.
It's going to, well, when it goes into that gemstone, it is going to bend. It is going to bend because we're going from a less dense medium to a more dense medium. Medium just means, air to water to honey to whatever. But if something is going from less dense to more dense, when it does bend, it will bend towards that normal, which again is that mythical line at right angles to the surface there. So if you want to get technical, we'll talk about N1 being the less dense medium, N2 is the more dense medium. Now, if you can see there, because the light is bent, is that incident ray the same as the refracted ray? No, because it's been bent. If it wasn't bent, we'd expect that to be going straight ahead there, and then you'd have a situation like reflected ray, but it doesn't happen that way. When it hits that more dense medium, it slows down, and the slowing down is what causes it to bend. So my way of explaining that would be like a great big long truck, and the truck has to slam on its brakes really quickly. What happens?
The tail goes.
The tail goes around because the front has stopped. It's slowed down. The back is still travelling what it was, so the only thing it can do is slew around. So that's exactly the same as what happens here. The wave at the front hits and it bends just like a truck when it's put its brakes on, because that's like the the truck going into a more dense area because it's hit the brakes and slowed right down. I don't know if that helps anybody, but it's the way I see it for this idea of slowing down. So if I'm walking in a swimming pool or I'm walking through honey, it's going to be a lot harder to walk through honey than it is through a swimming pool because the honey is more dense. So Snell's law takes notice and says, well, no, the incident ray and the refracted ray are not the same. But again, they are measured with respect to the normal. So there's the incident ray and there's the refracted, the bent ray, and this one is less than that one. What Mr. Snell worked out is if you've got two particular mediums and a wavelength of light, the ratio between the incident and the refracted ray, the ratio remains the same. So whatever it was for air and diamond, that ratio between the incident angle and the refracted angle will be the same for all diamonds within reason, at the same temperature, say, instead of, it could be different if you heat a diamond up to, 500 degrees Celsius. So what it's saying is for two particular mediums, the bending that will happen will be the same, will have the same ratio. So if I have an incident ray that goes into quartz, it's not near as dense, it doesn't bend nearly as much. If I put that light's going into diamond because it is more dense, it will bend more. So for two mediums, like air and diamond, or air and glass, or air and quartz, the ratio between those for each gemstone will be the same. So for diamond, the ratio between the two angles will remain the same for all diamonds, but it will be different than quartz, and it will be different than glass because each has its own ability to bend light. And this is important. We need to know about this. We know all of this now because that tells us how to cut a diamond with perfect proportions.
Is there a simplified formula of that one, like there is for like I equals R for the law of reflection?
There is. I wouldn't say simple, but yes, we've got one, and you get to know it. So what are the two things happen when light goes from a less dense to a more dense medium?
It bends towards normal.
And it slows down. Two things happen. So if we wanted to measure what's going on when that light enters a gemstone, we would know that we can either work out how much it is slowed down, or we can measure how much it has bent. Both ways are valid, and both ways you could be asked in your exam to work out, because this is to do, we end up with a refractive index, which is the bending of light for a particular gemstone, and each gemstone has its refractive index with respect to something like air. Okay, so, and this is the next important, I should have asterisks right at the top of this, because when the light is moving from less dense to more dense, it bends towards the normal. Now, obviously the opposite happens when it comes out, doesn't it? So if it's already in there at the more dense and it comes out into less dense, it's going to bend the other way and speed up. Yeah? So going into something more dense or coming out of something more dense to less dense, the same thing happens, but in one instance, the light will bend towards the normal. In the other instance, the light bends away from the normal. That's important too. So you always have to remember, so less dense to more dense bends towards the normal. When it's going the other way around, the incident ray is already in the more dense. When it goes into the less dense, so that angle there and that angle there have still got the same ratio, but it has now bent away from the normal rather than towards normal. So it's exactly the same as this going the other way. I should have turned that around. Can you see what I mean?
Why is the 1 and the 2 swapped?
Oh, it's just the way they because we're talking about this is the incident ray now, because we're already in the more dense. So that is the incident ray, and this is the refracted ray. Down here, this is the incident ray because we're already in a more dense,
Okay.
and that's going to be the refracted ray. So it's just the way they do it to talk about incidents and refracted rays. It doesn't matter how you call it, just so long as you know how it bends when it's going to more dense or less dense.
But why would it go from a more dense to less dense? Because normally it comes from air to heavier material,
Yeah,
right? So
but
why
if
would
I-
I have the reverse situation?
If I've got my diamond,
Yeah.
I've got I've got a wavelength of light going into the diamond.
That's dense.
When it's in there, I want to know what's going to happen when it leaves the diamond.
Oh, right, I see.
So what's going to happen to it when it leaves the diamond? And this is the way that it's worked out, because when it's then going from the light that's already in there to come out again, what's going to happen?
Okay. Thank you.
So if the incident ray is at the same direction as the normal, so if that ray going into a more dense substance is at 90 degrees, we don't get it skewing left or right, we just get it slowed down. So it's just slowed down because it's at the right, it's at that normal at 90 degrees, so it just slows down. But in every other direction, apart from the normal, it will slow down and be bent. So this is a solid piece of glass or whatever you like. But when the light, if it's perpendicular to that level there, and same coming out again, if it's perpendicular, we don't get the bending, but we get the slowing down and the speeding up. It does follow, believe me, it gets us somewhere. But I'll hammer on about less dense to more dense, towards the normal, more dense to less dense, away to the normal. It's really important when we get there. So here's our bit of glass with reflection. Here's our incident ray and our refracted ray, and it has bent towards the normal. Therefore, this one is less than the incident ray, yeah? But because it's the same medium, say it's glass, then that angle there is now its incident ray, and it bends away from the normal, so that incident angle is less than the refracted angle, which is the opposite of up here. So going into the gemstone, it bends towards. When it leaves the gemstone, it goes away from the normal. So we get this situation like this. So instead of thinking that the light's going to go straight ahead, it actually gets bent. So the wavelength that's come in and come out eventually are parallel but displaced. It's why when you get to a rock pool and you reach down to get a shell, it's not in the place necessarily that you think it is, because the light, when it's gone in, has been bent because it's gone from less dense to more dense. Okay? So that's what happens. And we're just talking about one wavelength of light there. So what would happen if this wavelength of light that I was talking about was at right angles here? What would happen? Go straight through. So it would in fact be the one line, but when it's at an angle, it's
Is that
just...
angle important? The angle of entry important?
Yes, yeah, because if it was like this, then it would still be displaced and have the same angle coming out, but there'd be more or less displacement. But you'd still get this towards and away from situation happening.
So when we're setting up testing, do we have to set it at a certain angle of light coming through?
No, because it's a bit more complex than that. But
Okay, that's fine.
But for a gemstone, the way it bends is all the same. So in fact, no, I think what you're saying was, so it doesn't matter on the incident angle really, because it'll come out the other side parallel but displaced, but it will be, so if we did it with glass or we did it with a diamond, the displacement would be different, but it wouldn't be for...
So we're measuring the amount of displacement.
We're measuring the bending, yes. Depending on which how we're using it. This is just showing you how. So when we look at that, you can do this at home. If you put a straw in air in a water, that's what it looks like. But if you actually put it in a glass of water, you can see that. And that's exactly why, because looking at it, it's been displaced, still parallel, but it's been displaced because it's changed. It's changed. Going into the water and then coming back to me into the air, because I'm looking at it in the air, I'm not looking at it in the water.
So would you explain the concept of parallel?
Well, that and that are parallel.
Oh, I see what you mean, yeah.
So it's not that and then a totally different angle.
Yeah,
It's been broken, but they're still parallel.
thank you.
That is a real life picture. It's had nothing to do with Photoshop. If you're up in the Arctic, or this was taken up in the top of England, if you've got particular situations, you get this optical illusion, and that's exactly what we've just been talking about. Because even though we've only got air there, we've got a change in density from very cold air to warmer air, and we get the light diffracted from the less dense to the more dense. So in fact, that's sitting on the water, but because of this particular type, it's called an inversion. But it's just to show you that this is what happens because we get this optical illusion because of the bending of light. Now, down the bottom here, you can't see it very well, but down the bottom there is an example on YouTube of a fish, and the girl draws how you can see it, and that's relevant because you get the same question in your workbooks.
Fish or the ship?
The fish, not the ship. That's just me showing you that these odd things happen, and it's because
I printed it, it's not there.
maybe well, maybe I had that in my thing and not on that, but in the new one you say you can add it to it. When I put this one up,
Okay.
you can add it to your slide. Okay, so it's just, and you can just, it's just a YouTube thing. If you don't want to watch it, you don't, but it explains, it shows you, here's the fisherman with a spear, here's the fish in the water. When he throws his spear and he threw it straight, where is the fish really? Excuse me, too much talking. I'll need a rose chocolate in it. Sorry about that. So that's just, yeah. You don't need to know how that works. I've just put it in there because it's an example of the light going from cold air to warm air, and that cold air to warm air means that you get bending of the light because it's changed from a less dense to a more dense, even though it's all air, and we're talking about, say, air in a gemstone, but it's the same principle. And every now and then some photographer does that and they think he's been playing around, but in fact it's a natural phenomenon that sometimes happens. Okay, so this is the one that is always in. This is the definition you really need to know. Now, we're talking about refraction, the bending of light, and we're talking about this hemisphere is our gemstone. So when the light is in that gemstone and it wants to come out of the gemstone, there's the incident angle and there's the refracted angle. So when it's coming from more dense to less dense, what happens?
Away
It
from
bends
Closer to the,
away. So the bigger that incident angle, so here we have, if we got bigger and bigger, it would bend more and more and more away from the normal until eventually it goes at 90 degrees. And if we go past that angle, it actually doesn't escape the stone at all. It actually is internally reflected back into the stone, and then following Snell's law of reflection. Now that sounds like magic and fancy footwork, but it's not. So I'll come back to this, but that angle is called the critical angle, which is for a gemstone like a diamond or a quartz, at the angle at which there's so much bending of the refracted way that it is at 90 degrees to the normal. So it's not really escaping the stone, and if we make it a little bit bigger, the incident angle a little bit bigger, the light does not escape because it keeps following that bigger pattern away from the normal, and we get total internal reflection. And that's what we want with a diamond, and that's how we use all the right angles so that if the light goes into that gemstone, it does not escape. It goes in, it bounces, and it comes back out and hits us in the face, so we get the brilliance of a diamond or whatever gemstone. So, but the angles have to be different. The critical angle is different for every gemstone. So how that light is bent is based on whatever gemstone it is that we're looking at. Now, that's a lot to take in, but that's your definition, and I'll show you some things on YouTube in a minute to show you exactly what does happen.
So why are they different then? Because the density is different. Is that why? Or is it the angle that the light's going
The angle, we're now talking about light going from more dense to less dense, but as you change the angle, it gets, the refracted ray gets bent further and further and further away. So this can only happen when we're going from more dense to less dense, because it's the only time when that refracted ray is moving away from the normal, okay? So any angle greater than the critical angle, the light will not escape the gemstone, it will come back in. So if this was my diamond and I put it on some writing, you could not see the writing through it because no light has escaped through the gemstone. If I put a cubic zirconia down, light does escape out the back, and so you can read. It's one of the tests you can sometimes do. It's called a read-through test, because with a CZ you can actually see the line through it, but with a diamond you can't, because we've got total, unless it's a truly abortionate cut, you will not get any light leaving it. So it is a little test that you can do, because no light will leave that diamond. Only come out to see us at the top.
So the CZ doesn't have a critical angle?
It does, but if we sometimes, with the critical angle means we'd have to cut them much too deep, and so we don't do that. So they cut a CZ so it looks like a diamond, so we do get some loss of light, because it's got a different set of angles that we have to work with. So diamond does, because it's so dense, diamond does this refracting, this bending really, really well. There are some others that do it as well, but diamond does it well. Moissanite does it well. Quite a few of them will do it well, and others like sapphire or quartz don't do it very well at all.
So that's when you've got to pay a bit of a hocus pocus with your angles and things like that to get as much bling as possible.
Yes.
Around.
Yes. Okay.
So the brilliant cut won't work best for all gems, is it?
So long as the brilliant cuts your 57 facets, but you've got to have the angles right. So
it works with all gems.
Sorry?
It works well with all gems.
Well, if I wanted to cut the quartz so I lost no, you'll see it in a minute, the critical angle when light will not escape for a diamond is 20 something degrees. For a quartz, it's very much higher than that, so we would have to cut the angles so differently. You might have a really deep stone before you're getting anywhere near a stone that's going to totally internal reflect. So this picture is just to show you that looks really crazy. It's just a laser beam, but the light hasn't left out of the fish tank because it has bounced back in, and then later on it'll go out there but this was the critical angle, greater than the critical angle. So if the angle was a little bit less than that, it would come up and it will go along the edge, and then after that it would come back in.
Does that have to do with the starting point of the source of light? Is that what it is?
It's to do with the angle, the angle of incidence. So you've seen, this is my little mag torch with a little light. If I want to look at a ring that's in a gemstone that's in a ring, I've got a little fibre optic thing, and I put the ring on there and I've got a light source. But there is no light here, only at the end. Oh, there's no light anywhere. So what I'm getting at, you've all seen this, the kids have in their rooms where they're floating around. But what I'm getting with this is, all your fibre optic cables are total internal reflection, because they've set the angle so the light will bounce, 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 bounce. No light leaves until the end when it comes out the top.
That one.
That's what a fibre optic cable does. So you don't lose anything outside, and that's what that is. You don't see anything till the end when it's let out for you to see. So this idea of total internal reflection is not just for our diamonds, it's out there everywhere that they make use of this phenomenon of total internal reflection. So they have set the parameters of this with the diameter, etc., so that when the light hits, it bounces off, so the angle's greater than the critical angle, and it just keeps bouncing inside till it gets to the end. Did you guys at home see that? They're asleep. Okay, again, it's showing you that it is not leaving. So, and when does it happen? When light is going from
More dense.
more dense to
less
less dense, because that refracted ray is bending away from the normal. It cannot happen the other way around. So if I get this one to work for you, it's not new, refraction. Okay, so this is water again. Just water. And she's got different colours of lights, different filters, so that you can see what's happening here. So when she turns it, we've got these up here, the light is escaping, and eventually the angle is such that it will come back into the water this way and not escape. So as the angle, so she's changing that angle now, so you can see if the angles are too small, all of the light is going to escape. When she goes the other way and makes the angle bigger, once we get to the critical angle of each of those wavelengths, it starts coming back into the gemstone. When you see it, you can believe it, because you'd think that it should all just go outside the water and not come back inside again. So it's all to do with your angles. And once because water is more dense than air, so if we've got the critical angle right, then that wavelength of light is going to come back into the water. This is I think this is the second one. Where's this one? Where's it? Oh no. There it is. Okay, so there's our gemstone, and he's got angles so that if you wanted to stop and read it, you could see the angles happening here. Just another example. There's piles of them online you can find yourself. And there's our incident angle. See at right angles, it goes straight through because it's at right angles to the normal. He's written normal up there. And as this angle gets bigger here, it gets wider up there. That angle there is wider. So for this gemstone, he's done 30-degree angle from the normal for the angle of incidence. Nothing happening yet. So for this glass hemisphere or whatever it's made of,
Well, it seems to have been faster.
say 40, so just past 40, so that angle of incidence is probably like 39 or 39.5 or something that would come along. Anything over that 39 or 40 is just past 40, we get total internal reflection. So for that wavelength of light and those two particular mediums, we know what the critical angle is.
That's measured from where he's got the light source, not from the light coming in.
We've got...
The 39 you're talking about.
Yes, because there's his 10 degrees, 20, 30, 40.
So say 40 just for...
So it's the angle between the normal and the incident angle. And then before that, the angle was between the normal and the refracted angle, once it's come back into the gemstone, we've got Snell's first law,
So these are both the same anyway.
so that those two angles would be the same with the reflection. But this angle here at nearly 40 degrees, just before this happened, was the critical angle, where the angle of refraction is at 90 degrees to the normal. Anything greater than the critical angle will come back and be internally reflected.
Right, so when you're cutting, you can't go below the critical angle. You've got to at least have the critical angle where it goes into.
Or more, yes, or more.
If you go lower, then it's.
You're losing, yes, you're losing light.
That's one thing I suppose.
But it's, but you've got to have this angle and that angle right. You can't, all of the angles have
that's
to
fine.
work.
Yeah. I couldn't work out why that happened.
Different angles for different substances, because each gemstone has got its own density and its own, so it will have its own critical angle.
So when they become internally reflected, they're basically equal but in reverse, like we have in the.
Once it's come back into the gemstone, it's no longer refracted, it is reflected.
Okay.
So that's why we have total internal reflection, because it has now come back in, it's no longer refracted past the critical angle. Yeah. It's physics, but if you can see it and you know how it works. So you need to know Snell's law of reflection and refraction, and I haven't given you a formula yet. Reflection and reflection, two of Snell's laws and how we say them. So with Snell's refraction, the normal, the incident and the refracted angle are going to be in the same plane, and the ratio between the angle of incidence and the angle of reflection remains constant for two media and a particular like two media, so air and a gemstones. For those two particular media and a particular wavelength of light, then we get a critical angle. So going back to all the wavelengths of light, you know, red's got a big long wavelength. There's a little tiny one for violet. In between is all the wavelengths of light. So each wavelength of light will bend light differently. So this I might call yellow light. So you saw from that this last one, she had different colour lights. They would have a different wavelength. So each of those wavelengths would cause a different refraction. So each of those wavelengths could have a different critical angle. So when you learned about the refractometer, we use a sodium light, which is a particular wavelength. So anybody who's measuring refractive index around the world will use sodium light, because if you used red and you used green, the angle of the critical angle would be slightly different. So if we want to standardize it around the world, so we all use sodium light, which is monochromatic. It's only one wave, well, it's actually two, but one wave of light, rather than all the different colors that we have with light coming from the sun. Now those diagrams also show you something, because we get onto a little bit later, because each gemstone will break up white light into its rainbow colours, its spectral colours, red, orange, yellow, green, blue, indigo, violet. Some gemstones will break up and give you dispersion more easily than others, not more easily, more easily to see. So the spread of all of the wavelengths of light can be more in some and less in others. So moissanite, strontium titanite, sphene, huge dispersion, huge numbers of colours, much greater than a diamond. Sometimes they can be so big that the stone looks fuzzy because you're seasick looking at it with all the colours. But the idea is that some gemstones, and then other gemstones, do this very, very poorly.
Very much, flat.
So now, how do we measure refractive index? So what are the two things? We're back to now, we're talking about light going into a more dense. Okay, so So when the light goes into from less dense to more dense, what are the two things that happen? Slows down and bends towards normal. Thank you. So if we want to measure that bending power, we can either do it by measuring how much it slows down, or we can measure the bending. Now, sometimes one way of doing it is much easier than the other way, but for your theory, you need to know it's both ways, and you need to know how to do it with both ways. So, if we're going to talk about it slowing down, the Ri is going to be the velocity of light in air divided by the velocity of the light in the gemstone or whatever. So we talk about the velocity of light in air is really 1. So everything else is more dense, so everybody's refractive index is going to be greater than 1. It has to be, doesn't it? Okay, now if we can't measure it that way, so in a question there's 3 parts to that. If you've got any 2, you can work out the other one, yeah? That works? So in an exam, if they gave you the velocity of light and an Ri, you'd be able to work out what the velocity was in the medium, or whichever way. They might give you the Ri and the velocity and tell you what that is, and you'd have to work out the velocity of light in air. But we know what that is, do we? 300,000 kilometres per second. So
Should we know that?
Well, yeah, put it in somewhere in the recesses. Yeah, put it in your notes. 300,000.
That
So
in vacuum, would that be faster than air though? Because the light speed 300,000.
300,000. That's how fast it will come in our atmosphere to talk to us. 300,000. Sorry.
What's the unit of measurement?
Kilometres per second. Ri is a ratio, so it does not have a measurement because we are comparing things.
So what's the 300,000?
That's the velocity of light in air. And when it goes into the light goes into a gemstone, it's going to slow down. So if we've got the comparison of those 2 velocities, that tells us the refractive index of that particular medium. Otherwise, we have to do it with the ratios. And remember I said the ratio between the incident and the refractive is always fixed. Now I can show you how they get this, and remember N1 is just air, N2 is the medium, the refractive index of those, and the sign is just mathematicians playing with triangles. Now there's a diagram in your notes that shows this. What you need to know is the refractive index is this ratio between the sine of the angle of incidence and the sine of the angle of refraction. Now sine just means, if you care, oh well here we go, first of all there's the speed of light. So I said 300,000 kilometres per second. 300,000 would be close enough. So if we actually said the speed of light is this, the speed of the gemstone is that, what is the Ri?
How do we measure that?
Well, we don't. This is why I'm saying that this is only for a theoretical thing, because we can't do that. We can't do that in the lab. But this is a way that it can be done if you've got sophisticated equipment. But we're not going to use that in the laboratory. We're going to use the angles, the ratio and the angles to get it. So, and that's the Ri of diamond. It's just, I've just made that up. But basically, that's the idea. So your Ri is always going to be greater than 1. So, and that's the way you do it. Okay, is everybody happy with that one? Now the second one is where we say that the ratio of those angles are equal. Now if you say that, if they ask you for a definition of the Ri in words or a formula, if you say that the ratio of the angle of incidence and the angle of refraction is fixed for a particular for 2 particular mediums and a wavelength of light, that is the correct answer. But mathematically, mathematically, when we're talking about bending and normals and everything else, the sine is just these, as I say, mathematicians playing. There's sines, there's cosines, there's tangents. Them playing with triangles that are, in this particular instance, it is not an equilateral triangle. So if I want to know the sine of A, I have to put the hypotenuse over the opposite one. So the sine of A is going to be just a number that is 17 over 15. I would look up a set of sine tables and it would tell me what it was. You do not have to calculate that, but that's where this sine comes from, because they work out with a compass. They can work out where cut-off points are, and they work out the sine of those angles to give us the ratio.
If there is a button on the calculators, the sign.
There is a sign button, but
Yeah.
you won't have to do that,
Yeah.
because if you're going to be asked to sort this out, they will give you a sine value.
So literally, all we have to do is 15 over 17.
That's to work out a sine. That's not to work out a refractive index.
Right.
Okay.
What does the sign actually mean?
Well, it's just proportions with the hypotenuse divided by this. So they do this with all triangles and maths to get cosines and tangents, and they use that with mathematical calculations when they're working out stuff. So I'm just showing you where the sine comes from, because it's just a relationship between sides of a triangle, okay? And that's how they've worked out sines, because the diagram in your notes uses a compass to draw a circle, and then they look at the angles, and they work out, because the ratio is the same, then the sines of the angles, and there will be a fixed ratio of the sine of the angles as well. So you don't have to know that. That's just for me to say this is where the sine comes from, because it's only talking about how you get a ratio of that over that, and they call it a sine of that particular angle. So, so the sine of A, whatever that angle is, the sine is point. So it's just a ratio again, because it's 17 divided by 15. So when they're working this out, if they've used a compass to go around there's our normal, and so we're talking about incident angle. So they've worked out that there's our triangle, and there's the angle we want. So they've worked out the sine of that triangle, and then the same here. That length there and that length there is the same distance along. Oops, sorry. So this is out of your notes where they're saying, all right, that length there and that length there are going to be the same. So we get that length, and that length gives us two triangles. And as I say, you don't have to learn that. This is only for those mathematical bods who want to know where it comes from. All you need to know is the formula, but this is how they've worked it out. So we've got an incident angle, we've got a refracted angle, and by using maths and triangles, we know what the sine of those angles are going to be. We don't really care, except that we know that the ratio between them is always going to be fixed.
How do we determine where the normal sits?
The normal is always at right angles.
It was at right angles, but it could be way to the left or way to the right.
Doesn't matter. There's a normal all the way along there, depending on the wavelength of light. So if the wavelength of light is coming out here, the normal would be there. It's just a mythical line. So we can do those angles. So that diagram is just showing you how they say that length is going to be the same as that length. So if we make those into triangles, we're talking about those angles, and that gives us the ratio that we want.
Jen, in terms of the definitions, they're optically rarer.
That means less dense. So optical rarer means less dense. Optically denser means more dense.
But we can just write
more dense, less dense.
All right,
is enough. Yeah, is enough. Is enough. I have an Italian son-in-law. Is enough, he says.
So,
in my opinion, yes, is enough. Sorry. So, no, he's the most darling man on earth. I'm not being rude. He's lovely. I have one daughter that's Italian and one son that's Canadian. They live across the world. I've got an Italian granddaughter who's 12, and she speaks very much like an Italian. Even though she hears all the Australian English at home, she still has a very strong Italian accent. Easy enough. So anyway, so this is just to show you from your notes that they're using triangles and measurements to get this formula, because all we care about is that the ratio between those two angles is always the same for the two media and a particular wavelength of light. That's your definition. That's all you need to know. Otherwise, you don't need to know any much further, except that if I wanted to look up sine tables, they're online. They give you the angle and they'll tell you what the sine of that angle is. So if you were given two sines in a formula, you can work out the RI. So with each of these formulas, so when light travels from less dense to more dense, that's going to be the sine of the angle of incidence over refraction, because that's the bending, the ratio we want. If it's going to be the other way around, does it make sense to reverse it? Yes, because remember I showed you that going in bends and going out is the opposite way and they're parallel. So if it's going from less dense, we put the incident angle on the top. If we're doing more from more dense, it's just the reversal. We only care about that when we start talking about refractometers. Because in refractometers, we've got one gemstone and we put the other gemstone on the top. So we've got two different denses, a more dense and a less dense, but it's not air. So we've got two mediums. So that one, this one is more about when we're talking about the refractometer. This one is when we're talking about the RI of a gemstone with air, because we're doing less dense to more dense.
Wouldn't the other one be, as you say, with two different media being denser than air, one's got to be less dense than the other, so wouldn't that be less dense and more dense?
But remember, the angles are going to bend the other way. The angles are going to bend the opposite way, depending on which way the light is travelling. So it has to be, and the ratio is going to stay the same, so it has to be up the other way. So the main one you want to learn is this one. Now, the next little bit just follows on from that very simple formula. But when more dense to less dense, I've put it upside down, and we only get the critical angle when we're going more dense to less dense. So the sine of 90 degrees is actually 1, because then we get an equilateral triangle. So so if we were looking at the critical angle, remember, is the angle that produces the refracted ray at 90 degrees. So if we put the sine of 90 on that top bit there, the sine of 90 degrees is 1. So there's the number 1. So under there will be the angle that produces that, the incident angle that would produce that thing. So the RI is going to be the sine over that and the sine over that. So the sine of the critical angle, we can swap those formulas around. That's easy enough to do. So the RI is 1 over the critical angle, or the critical angle is 1 over the RI. So if I told you that the RI of a gemstone was a particular thing, and you know that the sine of, for the critical angle, we know the sine of R is going to be 1. And if we're told that, we could then work out the sine of the critical angle, and then you'd look it up in a set of books. Online, one of those, and that would give you the angle. Okay, you're not going to be asked to do that, but you do need to be asked, you will be asked about these formulas and how you get the critical angle. So from that, it's very easy to get to this, because this is the angle, the refracted angle is the sine of 90 degrees, remember, because that's where it is. That's the angle that produces the refracted ray at 90 degrees to the normal.
And which one is the sine of the critical angle?
The sine of the critical angle, well, if we know the RI, we can work out the sine of the critical angle, or if we know the sine of the critical angle, we can work out the RI. Again, so we've already got one bit of information there, so if we've got one of the other ones, we can work out what the critical angle of a gemstone is, in theory. So if you know that one, the right way up, less dense the more dense, upside down for the other way, and then to get the critical angle, if you know that formula and your definition of your critical angle, you'll be cooking with gas, okay? You'll be doing well. That's the whole crux of this with respect to critical angle and what happens with wavelengths of light. We're not talking about particle, we're talking about the wavelengths, and this is how we get it. And so this goes on to, when you do a lesson on the refractometer, this is how the refractometer works.
The I is the
Incident angle.
incident angle.
So it's the sine of the incident angle over the sine of the refracted angle. And the refracted angle that gives us 90 degrees, that's going to be 1, and therefore we can work out that critical angle. And we care if we're a cutter, we care if we want to set up a refractometer so that we can measure RIs. So this is often a half-mark question. When we're talking about air in a gemstone, the higher the RI, the smaller the critical angle, and there are your definitions. Now, we're talking about a gemstone and air. If we were talking about a gemstone on the refractometer, we're talking about then the gemstone being the less dense, it's going to be the other way around, isn't it? So in air, the higher the refractive index, the lower the critical angle, which is why we can do wondrous things with diamonds.
So what did you say in air?
Sorry?
What did you say in air?
With the gemstone and air,
Yeah.
the higher the refractive index, the lower the critical angle. So we can cut diamond with, and now we know that's the critical angle, but we don't use that here. The angle of a diamond down there is actually about 41 degrees. So that is translated into more calculations to work out our angles to make sure that when the light bounces off, we're greater than 24 degrees inside. Physics, you guys know physics now. So the RIs there, we actually mentioned it a little bit before because cubic does not split the light into 2 rays. So we get 1 reading but we won't get that on a refractometer. But the other 6 crystal systems actually split light into 2 rays, so you actually record extra lines when we get to the refractometer. But that's just to show you that the difference between diamond and quartz with their critical angle is huge. And with glass, it depends what production of glass. It can vary because the production of glass can be different. We can have high lead glass, etc., etc. So the RI can vary with respect to glass, but these gemstones have got fixed critical angles.
So why does it vary with glass so much?
Because they make different compositions of glass. So that when the light goes in, the different compositions will have a different response to the light that goes inside. So give me Snell's law of reflection.
I is equal to R.
Yeah, the angle of incidence is equal to the angle of reflection. And how do we draw it? If you're asked to do a drawing, we do a surface, we do the normal, and we label surface and normal. And then where's the incident angle? But it's between the normal
and the surface.
And the incident angle.
Oh, sorry, yeah.
Between the normal and the incident angle, that angle, not the one next to the flat surface, it's between the normal, your incident angle, and your reflected angle is with respect to the normal. Okay, what's Snell's law of refraction?
Light bends away from the normal and slows down.
Well, the light, there is his law actually is that there's a fixed ratio between the angle of incidence and the angle of refraction. between two media, like air and a gemstone, at a particular temperature. So then we decide what's going to happen to that light. So you're right, if we're going from less dense to more dense, it bends and it slows down. And which way does that refracted angle bend? Towards the normal. Because it bends towards the normal, we'd never get to a situation where something crazy is going to happen to it. It has to bend away from the normal if you want to get internal reflection. So the only time you can find a critical angle is when the light is going from more dense to less dense. So they're the only golden rules for all of that.
Do you have that written somewhere?
Sorry?
Do you have that written somewhere, the law of refraction in simple terms like that?
Yeah, I'm sure somewhere I did. Constant ratio between the angle incidence and the angle of refraction for two media at a fixed temperature.
Cool.
Okay, and then you can go on.
It says in here, in the notes, it says, for two given media, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for light of one wavelength.
Yes.
Does that mean the same thing?
So, yes, so for two media and one wavelength, which is why.
Okay. Cool.
Okay, so I should write that in there because it's a constant ratio, which is the sine of the angle of incidence and the sine of the angle of refraction for two media, like air and diamond, for a particular wavelength, because as I said, if I use red light, it will, because it's a big slow one, it will bend differently than this tiny little red violet wavelength. Will bend it, and in fact, red bends it a little bit, the violet end bends it a lot. So we would get different refractive indexes. So when we talk about refractive index and the refractometer, we're talking about sodium light, which has a 589.3 nanometer wavelength, which you'll get to remember when we do the refractometer. But so we use as a standard a particular monochromatic wavelength of light.
So why were we inverting it when it comes from dense to less dense?
So if we're talking about air in a gemstone, the light's going less dense to more dense.
Yeah.
But if we're talking about the light already being in the gemstone, it's in the more dense, and it does the exact opposite when it comes into the less dense. So then we have the exact opposite of formula, because the angles have still got the same ratio, but to get them, you've got to do the formula upside down.
So that's part one, and then there's part two, yeah?
So this is the simple version. And then after that, you can write Ri equals sine I over sine R, when we're talking about a gemstone and air. So when you go through these notes that I think are hard to follow, you can write a series. So you can write, that is the very simple one in words. You can write Ri equals the sine of I over the sine of R, but you preface that as well by saying when light goes from less dense to more dense. So always when you're doing a question like that, you need to say from less dense to more dense, or the other way around, when you're talking about what happens to those wavelengths of light. Stunned silence. It really is, the idea is complex, but it comes down to some very simple formulas. And if you know both of Snell's laws, when is the only instance when we can get a critical angle? When the light is going from
medium dense to low dense.
More dense to less dense. Yes, same thing. More dense to less dense, because that's when the refracted ray is bending away from the normal, so that we can get it to come back into a gemstone.
So in the notes, it says the part two of that is the incidence and the refracted rays and the normal at the point of incidence lie in the one plane.
Exactly, just like the reflection. So with reflection, you get that. And so the incident, the reflected, and the normal are all in the one plane. You can't have one going off at a different angle. And it's exactly the same for the refracted ray. Both your rays are going to be in the one plane and the same plane as the normal.
Do we need to write that.
You do.
You do.
You do. That second part is just to be totally 110% correct.
Okay.
There's two parts to that answer. But they're not long, and it's the same for both of those. That bit about the two rays and the normal being in the one plane, that's the same. For two medium, that's the same. For a temperature, that's the same. So they accept that. One's reflection, one's refraction. And then when with refraction, we're going to have whether it's going from less dense to more dense or more dense to less dense. 7:30. Anyone need one of Nicole's chocolates? We can go further, but it might be just time to have a little.
So within the same plane is mainly for reflection, not refraction.
Both. Be in the same plane, all three bits. The two, the incident, the refracted or reflected, and the normal have got to be in the same plane.
What do you mean by plane, actually? That's why
Oh, well.
I'm listening to
Do we need to write that for the reflection one as well?
Yes.
Yeah.
For
write
both
that
of
for
them.
both.
There are two parts to both of them. But in one, the incident angle and the refracted angle are the same, plus the extra bits. And in the other one, the ratio of the angles remains the same with the other bit.
So the plane is just where it's at, yeah.
They're all in the same plane. You haven't got one coming in here and coming off this way.
Yeah.
So, what's the frequency of a wave?
It's
How
the
many
number
within
of
specific
troughs
time?
between.
Or the frequency is how many of those wavelengths you get in a particular period of time. And if I want to polarize a light, if the light's coming in this way, what else is the waveform doing as it's moving forward that way? That's the
Particles are moving all around.
Oh, yes, at right angles to the wavefront. So at right angles to the direction of the movement, in all those directions, you're exactly right, perpendicular to the direction of the wave is actually traveling. So if I polarize that light, what am I doing?
You're manipulating all the particles to move in one direction.
So yes, that vibration at right angles to the way it's going forward, we're only allowing one of those vibration directions to continue through a barrier of some description. Perfect. That's really good, guys. So we did that, and that's just to work out your critical angle. So we've just manipulated your basic formula for that one. And we said that one, that's always a half-mark question that's in there. If you remember diamond and quartz, they're really good. 24 and nearly double, like for 40.
Oh, well, we have to remember the actual critical angles and stuff?
Well, no, not really, but it's nice to know that diamond is less. When you're talking about gemstone and air, diamond is, and it's easy to follow because if it's got a small critical angle, we can do heaps with the cutting. If it's got a big critical angle, we're very limited. Yeah. So the smaller the critical angle, the better.
Yeah.
So the higher the refractive index, the more bending that happens in the gemstone, the more we like it. So, all right, I'll open the roses, and there's these that I opened as well, not knowing that Nicole was going to be nice to us, so whatever we don't eat, we can leave for the next one, so there's plenty there.
Did you bring snake?
I bought, it's a combination, it's a party pack, there's all sorts of bits in it.
So is this not right?
It's break time, and I have so many Easter eggs at home, I could have bought enough for all of us of Easter eggs, actually. It's absurd how many Easter eggs.
I know. I didn't give any chocolate this year. I decided against it.
I have small amounts of chocolate in my fridge.